Have you ever wanted to know whether an equation looks like this or this, but have been too lazy to graph the equation? I know I have. Well, do I have something for you? This is called concavity. This is whether an object has a shape or outline that resembles the inside of a circle. And there are two types of concavity. This is concave up, or, as I like to say, it can retain water, or concave down, which means it will act as a watershed.
Here we have a graph of this function. You see, at this point here it's concave down, and here it's concave up. But how do we find out? Where it starts to be concave up and where it starts to be concave down? To do this, we find the second derivative of the function. First derivative, 9x squared plus 12x minus 4. Second is the first derivative, and the second derivative is 18x plus 12. We need to set that equal to, the second derivative is 9x squared plus 12x minus 4, and the second derivative is 18x plus 12. To find the point where it goes from concave down to concave up, we set equal to 0. 6 does not equal 0, so it's crossed out. 3x plus 2 equals 0, so the point where it changes from concave down to concave up is negative 2/3. We know the second derivative when the second derivative is negative, it causes the slope of the line to become negative, as is shown here, where it is less than negative 2/3. The second derivative is less than 0. So the slope decreases over time, causing a concave down shape. When x is less than negative 2/3, the second derivative is also less than 0, which makes it concave down. And then as x goes past when x is greater than negative 2/3, the second derivative is greater than 0, making it concave up.
Okay, well, let's say we have a straight line and we need to find out the concavity of that. Y equals x. Well, we can obviously see that there's no concavity here, but since this is math, we're going to have to prove it. So we're going to use the second derivative test, which we have f of x equals x, and f prime of x will then equal 1. Then we have the second derivative of f of x equals 0. There's no equation for that, and it's just 0 the entire time. Therefore, it leads us to believe that the second derivative is going to be 0 from negative infinity to positive infinity, which then we can say that this line has no concavity in it. Okay. In conclusion, concavity can be used on just about any equation. And these are just some general rules for concavity. When you have an equation, what you first do is, to determine concavity, is find the second derivative. And you plug in the point which you are interested in, and if the second derivative is greater than 0, it's concave up. The second derivative is less than 0, it is concave down. Concavity is caused by the increasing or decreasing of the derivative of the original function, which is why we use the second derivative to determine how fast or slow, or negative or positive, the slope of the derivative is going, which helps us determine the concavity. If it's concave up, f prime is increasing. If it's concave down, f prime is decreasing.